In this section, we'll be discussing growth and decay. In particular, we're going to use separation of variables, which is a topic that we discussed a little bit in the last section, and we're going to discuss in even more detail in section 6.3. We're going to use separation of variables to solve a simple differential equation, and then we're going to apply that solution to multiple examples of exponential growth and decay. All right, let's jump in. The first is a very basic differential equations question, and it says y prime is equal to 2x over y. And you might remember that a differential equation is an equation that involves a derivative, and we see that here, y prime, and the unknown variable y usually. It doesn't have to, it's really any equation that involves a derivative. All right, and so this particular example says that the derivative of y is equal to 2x over y, which means if we knew what y was, we could take its derivative and put it on the left side of the equation, and then take 2x divided by whatever the original y was, and the equation should be balanced. They should be equal. All right? So our job in solving a differential equation is to find y. We have to find the original function y that makes that equation true. So if I look at this first equation, the first step is to rewrite y prime as dy dx. I'm going to use Leibniz notation. So dy dx equals 2x over y. Then I'm going to integrate both sides. Nope, I'm sorry. Before I integrate, I have to separate the variables, as it says here, separation of variables. So I'm going to multiply by y, get all the y's on one side, and multiply by dx, so I get the variable x's on one side. Now I'm going to integrate both sides. All right? If I integrate y with respect to y, then I raise the power 1, divide by the new power, I get 1/2 y squared. On the right side, I raise the power of x. I'm integrating x, a function of x with respect to x, right? So that works, it's fine. Raise the power, divide by the new power, I just get x squared. Then technically, both the left side integral and the right side integral would have a constant. These are indefinite integrals. So I could put a plus c here and a plus c here, but I only need c on one side or the other, because when I add them, when I pull them together onto one side, I'm going to have just one constant anyway. So I'm going to write it only on the right side. This is pretty standard. All right? Now I have a couple of options. I'm not done. A lot of students will stop here, and that's a mistake. You're not finished until technically you find and isolate y. All right? So I could do that, just multiply by multiply by 2, and I get y squared equals 2x squared, plus, you could write 2c, but when you multiply a constant times 2, if I don't know what that constant is, I might as well just still call it some unknown constant. I'm not happy with the way this is looking, so I'm going to rewrite it. There we go. So 2 times c is still just some constant c, so I'm going to leave it that way. All right. Then I would take the square root, and y equals positive negative square root of 2x squared plus c. Now I've solved for y. Y is isolated, so I've answered the question. I technically would be done. Now, I do want to point out a couple of details here. First, a lot of students would leave this plus minus off when they take the square root. That's a rookie mistake, an Algebra 1 student mistake. Don't do that. And secondly, sometimes, however, a problem will give you details that will tell you whether or not we're supposed to use the plus or the minus. That's where it gets critical. If it's supposed to be only a positive, in other words, if y is in quadrant 1 or 2, then you would use only the positive. If y is in quadrant 3 or 4, then you would use only the negative. Very rarely in some applied problems do we put plus and minus. All right. So that's one note. The second note is I didn't necessarily have to solve this for y. If this was a multiple choice question or something, some problems would have c solved for. Because if you notice, if you solve for c, what you're looking at is an ellipse. This formula actually represents an ellipse. All right, let's move on. Growth and decay models. This is where the bulk of the lesson today is going to focus. In many applications, the rate of change of y, the variable y, the rate of change of the variable y is proportional to the value of y itself. That statement right there is basically the foundation statement for this lesson. All right? The rate of change of the variable y. Well, the rate of change of the variable y is expressed, especially if it's changing over time, as dy dt, the derivative of y, the rate of change of y, dy dt, is equals proportional to the value of y. Okay, well, whenever we talk about proportionality, especially you might remember in Algebra 1, direct proportionality, we've got what we call a constant of proportionality. So you might have heard a statement like, y is directly proportional to x. And you would start by writing y equals kx. Or you might hear y is inversely proportional to x. And then you'd go y equals k over x. Inversely proportional, right? These were pretty common formulas. You use them on the SAT, ACT. They showed up all the time in Algebra 1 and beyond at this point. Well, the same thing is true here. In our statement, we've got proportionality going on, and we need a proportionality constant. All right? So dy dt is equal to k times y, some constant of proportionality times the original value y. All right? So it says when y is a function of time, the proportion can be written as shown. So this is our differential equation, and our job is to solve this differential equation. So if I separate the variables, all right, I'm going to start that way. Let's say I divide by y on both sides, and that leaves me with dy. If I multiply by dt, 1 over y dy equals k dt. Remember, k is a constant. We don't know what it is, but it's not variable. It's not changing. Y is changing, and t is changing. Time is going on, and as time changes, y changes. So those are variables, but k is going to be a constant. We're going to treat it as a constant. All right, so how do we solve? We integrate. Integrate both sides. And if I integrate the left side, notice it is natural log, right? ln absolute value y is equal to is equal to kt, right? This is a constant, and so this is the integral of, technically, if this was like, I'll go off to the side here, if I was dealing with, say, the integral of 3 dt, then my answer would be 3t plus c, right? So that's what's going on here. The integral of k, 3, some constant, k could be 3 for all I know, I don't know what it is, but times dt is kt plus c, right? Plus some constant. All right, now I can exponentiate to try to solve for y. My job is not done until I have isolated y. So if I exponentiate, I'm going to get y down on the bottom line here. Absolute value y is equal to e to the kt plus c. And this is where it gets a little bit tricky, right? Using the laws of exponents, I can split this apart. We don't normally do this. This seems a little counterintuitive, but it is true, nonetheless, that e to the kt times e to the c, when you multiply like bases, you add exponents. So this statement on in the middle here is equal to this statement. They're true. Then we could say, okay, well, e to the c, e is a constant, 2.718 and change, and c is a constant. So together, e to the c is just some new constant. Don't know what it is, but it's a constant. So I'm going to just call it c. And then I'm going to move it in front. c e to the kt. All right? And there we have it. The solution to this basic rate of change of variable y is proportional to y, this basic growth formula, or decay formula, that works for decay as well, is equal to c e to the kt. That theorem is shown in all its glory down here. And I will state that this is what we call the law of natural growth decay. Law of natural growth or decay. All right? K, this constant here, is what we refer to as the constant of proportionality in the dy dt, or up here in the y equals kx or y equals k over x. But really when it's solved, when we've solved for y, k is what we refer to as the relative growth or decay rate. Relative growth or relative decay, depending on the situation. All right, if k is positive, then the value of y is increasing. If k is negative, then the value of y is decreasing over time. All right, and that is stated here. Now, I should note also, y is positive. In natural, real situations, real world problems, we're not talking about negative amounts of an object. All right, we're talking about positive amounts. You can't have a negative population, or you can't have negative bacteria cultures, right, or negative rabbits, right? We are talking about things that are growing or shrinking exponentially. You can't have negative radioactive substances. You're going to have some amount. So this absolute value is pretty pointless. It's true that it needs to be here in the equation when we're solving mathematically, but in an applied sense, we can drop the absolute value of y because it is not needed. All right. So they say y is greater than 0. The rate of change of y with respect to t is directly proportional to the amount of the object. I didn't really hone in on that a whole lot, but when we apply this idea, you think about it, you can't have population growing if there aren't initially people to populate, right? And I should note, if you've got 1 million people in an area, that's going to grow faster than if you only have 2 people or 8 people. The population will grow faster. All right, so the population, the amount of a population, is directly proportional to the number of people in that population. Same is true for things like bacteria cultures, right? If you've got 8 bacteria cultures or 20 bacteria cultures, that's going to grow slower than if you have 5,000 bacteria cultures. Or a radioactive substance, if you have 30 milligrams of a radioactive substance, that's going to shrink faster than if you only had a half a milligram of a radioactive substance. All right, so these things are exponentially growing or exponentially decaying depending on the amount, proportional to the amount that is present. And you've seen this already in a very, very frequent application. In fact, I think we did it in the last section, in accounts and money-bearing accounts. The amount of money in an account grows faster if you have more in the account. If you have $1 million in an account, you're going to earn more money than if you only put $100 in the account, and so on. And take note, this is very similar, right? You're familiar with your formula, A equals PE to the RT. Well, guess what? The PERT formula, the amount of money in an account, is equal to the initial amount times the growth rate times the amount of years. E to the growth rate times, I forgot the E, but E to the growth rate times years. This is not an unfamiliar scenario. And it kind of gives us a little bit of a hint. So guess what? C is the initial value of y. In the same way that it is the initial amount in an account in our PERT formula, C represents the initial value of y. If you let t be 0, this disappears, right? The e to the kt disappears, and you're just left with c if t is 0. All right, so I think we beat that about to death. We've gone through every detail of that. Let's start to apply this. All right, here we go. Exponential growth model. Our first example here says the rate of change of y is proportional to y itself. As soon as we read that statement, we know we can use our y equals ce to the kt. Why do we know that? Well, because they have said the rate of change of y is proportional to y. So if I literally interpret what I've underlined there as a statement in mathematical terms, this is the statement, and we just did the solution to that right here. All right, so that means we can just start plugging in values. This This first statement here says when t is 0, y is 2. Well, they just gave us c. c equals 2. If I let t be 0 and y be 2, I'm just left with c equals 2, the initial value. All right, so if c is 2, then I can go straight to trying to figure out k. This group of information here will let me find k. All right, I can use to find k. And you'll find that most of these problems are about setting up the model and then finding the specific model, meaning finding k, finding c, and then using the model to evaluate for either some point in time or some value y after time has passed. All right, so here we're told when t is 2, y is 4. So I can say, okay, well, 4 for y is equal to 2 for my c. Just notice this 2 is the constant c. E to the k times 2 for 2 years. So this 2 is the 2 years, but this 2 is my constant c. And it's pre-count. I need to solve for k. Divide by 2. 2 equals e to the 2k. Take the natural log. Natural log of 2 equals 2k. Divide by 2. All right, so k equals really 1/2 ln of 2. And if I take that a little bit further, I can use the law of logarithms here, the power rule for logarithms that moves the 1/2 onto the exponent of the 2, which makes that square root. So ln square root 2 is one way to write this. All right? So if that's the model, or that's the k value, then my model becomes, if I plug in here, my model becomes, let me change colors here. Let's use this. Y equals 2e to the ln square root 2 times t. So there's my model. And now the problem says, final statement, or final question, I should say, what is the value of y when t is 3? Okay, well, I'll just let t be 3. Y equals 2 e to the, if I change it, 3, oops, 3 ln square root 2. Plug that in a calculator, and you get 5.657. 5.657. And that is our answer. Now, I will note first, with the exception of writing this differential equation here, none of this was calculus. All of this was a pre-cal problem. This is the same problem you could have gotten in a pre-cal class, even in the Algebra 2 class, if you got this far in Algebra 2 and you did applications of exponential stuff. All right? You found k, and then you put that in your model, and then you use the model to find a value they asked for. That's a pretty standard pre-cal question. The calculus was what we did earlier when we solved this general law of natural growth and law of natural decay problem. All right? The second thing I'll note is the model. They've given you the graph. It says if the rate of change of y is proportional to y, then y follows an exponential model. You've got the exponential model shown. At time 0, you've got 2. After time 2, you got 4. After time 3, we got 5.657. There it is. And they also changed the exponent k, our ln square root 2. They changed to a decimal, 0.3466. I would strongly recommend that you carry a lot of decimal places if you're going to do that. And then one final note, you can read this here. It says, using log properties, you could rewrite this base to be base square root 2. All right? Totally possible to rewrite your base so that it is not base e. We see that pretty frequently, right? You can take this expression, and this is technically just square root 2. Right, because e to the ln is square root 2, and then you've got that t still sitting up there. So square root 2 to the t. Another way to write that. All right. This box here is just a list of the half-life for certain isotopes, certain radioactive substances. All right, doesn't have to be radioactive, just certain substances. Or materials. This is not something you have to memorize, this red box. I know I boxed it in red, and I've said a long time ago that if we've got things boxed in red, you should memorize. This is not true about this stuff. You can look at this at any time. You can freeze the screen. You can come back to this video. You can look this up in Google it if you want to know the half-life of these objects. But the half-life is given for each of these objects. Pretty interesting. The lifespan of uranium, for instance, this first one. 4.47 billion years for uranium to be cut in half. What it means is if you started with 100 grams of uranium, by the way, 100 grams of uranium would be enough to kill pretty much anything in the city of Houston if it was to be released into the air. But if you had 100 grams of uranium and 4.47 billion years passed, then that 100 grams would be reduced to 50 grams. It takes that long for it to be reduced by half. Plutonium, 24,100 years. Carbon is often referred to in lots of movies and references all over the place because carbon is how we date things of antiquity that were alive at one time. If something was alive, then it had carbon in it, and so, that the carbon date a plant life, or the carbon date a fossil of some sort of crustacean or sea creature or dinosaurs or people, whatever. Carbon dating, 5,715 years for carbon-14 to be cut in half. All right, you've got all the way down to nobelium, 25 seconds, half of it. Cuts in half every 25 seconds. All right. One final note here. If things are always, this is Zeno's paradox, if you're always just cutting in half, you're never actually subtracting the whole value, but only cutting a value that was there in half, then you're always going to have some, even if it's just minuscule, some amount of that substance present. And all of us have, for example, because of radiation testing, all of us have a small, insignificant amount of plutonium. Well, actually, I don't know if it's plutonium. We do have radium in our bodies. Obviously, we all have carbon and so on. But radioactive substances are in everybody's body because of nuclear testing and stuff in the air and things. But it's so small that, well, at least we hope it's not causing any problems. All right, moving on. Our radioactive decay problem here. 10 grams of plutonium isotope were released in a nuclear accident. How long will it take for the 10 grams to decay to 1 gram? All right, well, they told us 10 grams. There's our initial value. That's our C. So we're already there. It doesn't actually say it in this problem, but this is a law of natural growth, law of natural decay problem. Because it's just a radioactive substance that's decaying over time. So we can use our general formula, y equals ce to the kt. All right, and so we know C is 10 already. So let's start plugging in. They tell us that we're starting with 10, and the half-life of plutonium is 24,100 years. So if I started with 10, then I'm going to have 5 after 24,100 years. All right, so I start with 10. I'm going to get down to 5 if T is 24,100. And this, of course, allows me to find K, right? So if I divide by 5 or divide by 10, I get ln of a half. I'm going to write ln of 0.5 is equal to, there we go, is equal to 24,100 K, all right? That's what happens when I divide by 10 and then take the natural log of both sides. And then if I divide by 24,100, I can isolate K. All right, so I've got K. By the way, if you put this into a calculator, because this is something that is taking forever to decay, you're going to get something like negative 2.876 e to the negative 5 is what you would see. That's a 6. It looks like a C. 2.876. Remember, that e in a calculator is technically times 10. So it's really times 10 to the negative 5 power, which is negative 0.12340 2876. All right, as a decimal. And this thing is decaying because of the negative, and that makes sense because it's radioactive decay, but also decaying very slowly, right? 24,100 years. So our relative growth rate, relative to the amount there, is really a small number. All right, so now our job is to go on and say how much is there, in, how long will it take? So find t when y is 1. So if I set y to be 1 equals 10 e to my technically ln of 0.5 over 24,100 times t, and my job is to solve for t. Again, pre-calc. Divide by 10, divide by this k value, and I've got t. All right, so t would be equal to ln of 1/10 over, I'm going to go ahead and write the decimal for k, negative 0.1234286. And if I solve for t, I get 80,058.467 years. Takes 80,000, almost 80,060 years for 10 grams of this plutonium to reduce down to 1 gram. All right. A little note over here in a conventional nuclear reactor, 1 kilogram, which is 1,000 grams, right? 1 kilogram can generate enough electricity to power 900 homes for a single year. All right. Little side note. All right, moving on. Population growth. An experimental population of fruit flies increases according to law of exponential growth. Boom, there we go. As soon as we get that statement, increases according to the law of exponential growth, we know that we can rely on our model y equals ce to the kt. All right? All this is pre-cal. We do not have to go back to calculus. There's no differentials. There's no equation. There's no integrals or derivatives here. We've just got a basic exponential growth formula. This problem says there are 100 fruit flies after the second day of an experiment, and then there are 300 after the fourth day. Notice what we do not have. We do not have C, because we have the amount after the second day, and then we have the amount after 300 flies after the fourth day. All right, so really we have two formulas here. We know there's 100 after 2 days, so 2K, and then we know that there are 300 after 4 days. Excuse me. All right, so we've got really a system of equations going on here. I'm going to take the left one, and I'm going to solve for C. So 100 divided by e to the 2k is C. And technically, I could write this as 100 e to the negative 2k. If I just want to bring this e to the 2k up, I can give it a negative exponent. So now that is going to go in for C in this formula. So 300 equals C is 100 e to the negative 2k times e to the 4k. So I have replaced this C with the expression I had for C here, just a simple substitution. All right, now I'm multiplying like bases. All right, so this turns into 300 equals 100 e to the 2k. Multiply like bases, you add exponents, and so negative 2 and positive 4 makes positive 2. Solve for k, right? And I divide by 100 and then take the natural log and then divide by 2. Hopefully you're seeing this pattern here. It's the same pre-cal steps over and over and over. Divide by 100, take the natural log, and then divide by 2. So k is equal to 3, ln of 3. I'm skipping some steps here. I just said it orally. Divide by 100, take the natural log, and then divide by 2. So 300 divided by 100 is 3. Natural log of that is ln 3, and then divide by 2. K is equal to ln 3 over 2. All right? So then the question says, if I'm answering the final problem here, it did ask me to approximate how many flies were in the original population. So in other words, y sub 0, the initial amount, y sub 0. Or, what are they really asking for? C, right? The initial amount of flies, y sub 0. So if I take this k value and plug it in here, I can find C. Here we go. 100 e to the negative 2k. Negative 2 times my k value is ln of 3 over 2. All right, and all of that is equal to C. So if you look here, that 2 cancels that 2, and then e to the ln, those are going to cancel, all right? And you know what I messed up? Well, that's okay. It's still going to be, when you divide, it's still going to work out. I'm really just going to take, if you simplify all of this, I'm not going to go through all this because I'm kind of out of space, but if you simplify this, you're just going to end up with 100 divided by 3. So C is equal to 100 over 3, or 33.333 if I'm going to 3 decimal places. But the fact is, we're not going to have partial fruit flies. We're going to approximate this to about 33 fruit flies. All right, the initial amount was 33 1/3 fruit flies. And you can look over here in the graph. At time 0, they got 33. At time 2 days, they have 100. And 4 days, they have 300. All right. They also approximated the K value to 0.5493. If you were to take ln of 3 over 2 in a calculator, you're going to get 0.5493. Okay, let's move on. Before I move on, I should note, this was a systems of equations problem. This was not your standard run-of-the-mill population growth problem. We had to create a system and solve. Okay, moving on. Declining sales. 4 months after it stops advertising, a manufacturing company notices that its sales have dropped from 100,000 units per month to 80,000 units per month. Okay, well, guess what? They just gave us C. We start out with 100,000 units. And after 2 months, at t equal 2, no, I'm sorry, after 4 months, I knew that would seem wrong. After 4 months, because it says 4 months after 4 months, the amount is 80,000. All right. The sales follow an exponential pattern of decline. Bingo. Now we know we've got y equals CE to the KT. All right. As soon as we know that, we can plug directly into our formula and start finding what they asked for, which is what will the sales be after another 2 months? So what will the sales be after 6 months? Another 2 months means t equals 6. All right, because we started after 4 months and we got 2 more months passing. Okay, so here we go. If I plug into this formula, I've got y equals 100,000 e to the, tell you what, we can go ahead and say if y is 80,000, if y is 80,000, then I can put 4 in for t and solve for k. All right? So if I divide 80,000 by 100,000 and I isolate the k value, I'm going to find k is equal to natural log of 0.8. By the way, natural log of a proper fraction like 0.8, which is 4/5, is a negative value. And then I divide by 4. So again, that's solving this for k. You should get this. And so my model becomes y equals 100,000 e to the ln of 0.8 over 4. And if I want to solve for t equals 6, I would just multiply that by 6. Plug that into a calculator, and you're going to get approximately 71,554.175 units. All right, they asked us what will the sales be after another 2 months, so we need to let t equal 6 months. All right, 4 plus 2. And there we go. Pretty quick. Pretty quick problem. Standard. Oop, that's not working. Let me get rid of that. Standard growth and decay. What in the world is that doing that? Standard growth and decay problem. There we go. All right, again, they've given us the graph over here, starting with 100,000. After 4 months, we're at 80,000. After 6 months, we're at about 71,500, which is really about what this is. Okay, let's move on. Our last discussion, last example here is about Newton's law of cooling. I should note before we go any further that Newton's law of cooling is not just for cooling, it actually works for heating as well. So we can take an object and heat it up, and it's going to follow the same models. In examples 2 through 5, we did not actually have to solve a differential equation. All right? We did this in the first example, the proof, and then we used the solution to this, which again was our y equals c e to the kt. All right? That was our solution to this. We used the solution for all the other examples. The proof was done in the first beginning, the beginning of the problems, before we did any of the problems, and then we used that. And it demonstrates really a solution by separation of variables. The next example, using Newton's law of cooling, states that the rate of change, let's break this down, the rate of change of temperature of an object. Let me write that statement that I just underlined in mathematical terms. The rate of change of temperature of an object, where capital T is the temperature and lowercase t is time passing. All right, is equals proportional to the difference between the object's temperature and the temperature of the surrounding medium. Okay, so is my equal sign. Proportional to, I need a constant of proportionality. Proportional to what? The difference between the temperature of the object and the temperature of the surrounding medium. We call that capital S, or the room temperature, or if it's in an oven, the oven temperature. If it's in a refrigerator, the refrigerator temperature. It's important to note, again, S is the temperature of the surrounding medium. All right. Temperature of surroundings. And it is also constant. The surroundings do not change. We're going to assume that the surrounding is constant. If it's in a room and it's 72 degrees in the room, then it's always 72 degrees in the room. If it's it's in an oven and the oven is preheated to 400, it's always 400 in that oven. All right. Obviously, there could be some minor variances in temperature, but ultimately we're going to consider the temperature of the surrounding medium constant. Temperature of the object, that's varying. That's changing over time. The capital T is changing over time. And T, of course, time is changing. K, our constant of proportionality, is also constant, clearly by the definition. It is not changing. This is a value that stays. All right. So that is the general differential equation that's created by the statement for Newton's law of cooling. The solution we're going to work out in this next example. It says, let Y represent the temperature in Fahrenheit of an object in a room whose temperature is kept constant at 60 degrees. All right, well, we know our S, right? So if I'm writing this as a differential equation then I have dy, I'm sorry, let me back up a second. I'm writing this as a differential equation. The important thing to note is that they changed variables on us. Y is the temperature of the object. And so instead of using capital T, like this general model suggests, we're going to change the T to Y. So dy dt is equal to K times Y minus, and in this case, we are told the temperature of the room is constantly 60 degrees Fahrenheit. So 60. All right, there we have it. A little chilly in the room. Is our general model. Problem says the object cools from 100 to 90 in 10 minutes. How much longer is it going to take to decrease to 80? Well, in order to solve this problem, we have to know Y. We have to solve for Y. All right, and solving for Y is going to have to be done using separation of variables, which we've done in a couple of problems already. So let's jump to it. We got to get all the Y's on one side and all the T's on the other. I get 1 over Y minus 60 dy is equal to K dt. Integrate both sides. The integral of the left is the natural log of absolute value, y minus 60. And the integral of the right is kt. And of course, if I put the constants from both sides together, I get a c on one side. The truth is, at this point, a lot of books and a lot of people would say, okay, I know I'm going to be moving on and I'm going to be manipulating and I might have a different C. So I'm going to, at this stage, call this C1, and then maybe later I call it C2, or maybe I drop the subscript and I just call it C. All right, but it's going to be identified by a different value or a different variable throughout the problem because we're going to make some changes to it. You don't have to do that. You could leave it as C. Again, you do not have to be special about the way you label this constant. You can call it C here and then keep calling it C even though you've changed whatever that constant is by multiplying or adding or something. All right, and I'll point that out. We're not done until we solve for Y. We got to isolate this equation. It's not so easy for a lot of students, but the process gets very repetitive if you've done this enough times. We're going to start out by exponentiating. All right, and if I do that, I get absolute value y minus 60 on the left, and on the right, e to the kt plus c, or c1. I will note here that we know that y must be greater than 60. All right, how do we know that? Because this is an object that is cooling in a room that is a constant 60-degree temperature. The object starts above 60, and it's never going to get below 60 if the room temperature is 60. All right? So y must always be greater than 60. If y is greater than 60, then this expression is always positive. All right? So technically, if y is greater than 60, then absolute value of y minus 60 is equal to just y minus 60. I can drop off the absolute value. All right, I'll point that out here. So I can leave off the absolute value from this point on. So going back to my solution here, I'm trying to isolate y. Really, I need to get that 60 over. I could just add 60, but I can also clean the left side up, right side up. This is y minus 60 is equal to e to the kt times e to the c1. And why? Well, for the same reason we were able to split this up earlier in the lesson. Multiply like bases, you add exponents, so this expression is technically the same as this expression. And in that case, e to the c1 is just some new constant, c. So I've got y minus 60 is equal to c e to the kt, or y is equal to 60 plus c e to the kt. And there we have it. We've got our model. This is not the answer to the question. This is not the solution to this problem. We haven't found the solution to the problem yet, but this is the general model for which we will work off of. Note, it's not quite solved for yet either, because I don't have c and I don't have k. My only variables should be y and t. But we did a lot. There's a lot of separation of variables work going on here. All right, again, we're going to do some more of this in the next section, 6.3, but for now, it's important to see there's some good work being done here to isolate y. Okay, at time t equals 0, given in the problem, at t equals 0, the initial temperature was 100. So if I set y to be 100 and t to be 0, I get, really, c is 40. 40. All right? And if c is 40, then I can take this model, oops, make that look a little nicer. Then I can take this model and get a little bit more specific. 40 e to the kt. Still don't have it broken down all the way. I don't have the model perfectly solved for because I don't have k yet. I'd have to go back up and look at more of the information. I know that if t is 10, right, at this stage I can say, okay, well, at t equal 10, y is 90. And then I could plug in 90 equals 60 plus 40 e to the 10k. And I can solve for k. All right? This is getting very repetitive at this point. We have done this sort of a problem now so many times in this. I'm not going to finish this problem. All right? You can do that. Finish the problem, find k. You're going to find k to be, as a decimal, approximately what you see right here, negative 0.02877. And then if you plugged in, the last part of the question says, how much longer will it take the temperature of the object to decrease to 80? All right, so if you plugged in 80 for y, once you found k, if you let y be 80, then you could find t. You could isolate t. Again, a little bit more pre-calculus to be done. I'm not going to do all that. The answer's over here after the temperature's going to get to 80 after about 24.09 minutes. All right. What I do want to point out is this general statement that we have proven here. The solution to this differential equation for Newton's law of cooling is essentially y equals the initial surrounding medium temperature plus the difference between the initial temperature and the surrounding medium times e to the kt. I kind of ran out of space there, but there it is. All right. If you look at this formula, we ended up finding that c was 100 minus 60, because when you put 0 in, the e disappears, the statement disappears, and you're just left with subtract. All right. You subtract and you get 40. So 100 minus 60, the initial was 100, and 60 was the surrounding medium. There's our c value. All right, so this differential equation for Newton's law of cooling is solved with this statement. Now, most people don't memorize this, but if you did have it memorized, it would save you a heck of a lot of time. Wouldn't have to do all this mess. All right, just pointing that out. Okay, there you have it. There is our lesson on growth and decay, and in particular, some good examples about how we do separation of variables. More on that in the next lesson. I'll see you then.